SwayamPrabha. Digital India. Educated India.
Dear learners, I welcome to this course Applied Thermodynamics, Refrigeration and Air Conditioning, Module 5. Overall, there are 6 lectures for this module. In the first 2 lectures, we have discussed about vapor compression refrigeration systems, part 1 and part 2, and in this lectures we mainly focused on refrigeration cycle as well as heat pump cycles. Today we will start the lecture number 3, that is a new topic, absorption, refrigeration and refrigerants. Okay. So, under this lecture we will discuss upon some important aspects of vapor absorption refrigeration, how it is different from vapor compression systems. And also of course, this vapor absorption refrigeration is not widely used, but it has its own importance, and in particular there are 2 types of vapor absorption refrigeration system that are commonly used in practice. One is ammonia water systems, other is the lithium bromide water system. And towards the end of this lecture, we will discuss about refrigerants and its nomenclature. So, first of all, let me start the vapor absorption systems. Let us see that how this vapor absorption systems is different from a vapor compression systems. So, if you recall our analysis that a vapor compression systems consists of evaporator, compressor, condenser and expansion valve. And one more important aspect here is that we have a compressor, and this compressor takes our majority of our heat input, and in fact it most of this power that comes from the electrical power, and which is in our sense we call this as a work as a input. But many times what happens, there are some instances that if at all we want to use this instead of work as input, if you can think of some kind of heat as a source to run this system, then we can think of this vapor absorption refrigeration. So, what does it do is that here the entire compressor unit of a vapor compression system is replaced with a pump, and this pumps takes minimal power, and at the same time 2 additional components gets connected here. One is generator, other is absorber, and other components like condenser and evaporator remains as it is. And the circuit combination goes like this, that if you look thermodynamically, we have some source that takes at which is maintained at T1, and the generator takes Qg amount of heat, and we have also region where it is maintained at means for the space which needs to be cooled, heat is get extracted and goes to the evaporator. And what does this condenser and absorber, they operate at some intermediate temperature T2, in which heat is rejected. So, basically from 2 sources heat is getting added into the system, and in one sources heat is getting rejected out of the systems. So, in a sense that then there is no electrical work in the form of work or high grade energy, rather we are entirely using heat sources as the source of input to drive the systems. This is one of the important aspects of a vapor absorption systems. Other important aspect of this is that when you look at this refrigerant in a vapor compression system, this vapor refrigerant continuously circulates within this vapor compression circuit, and in evaporator it takes the heat from the source and it becomes vapor, and in the condenser it releases heat to the surroundings and it again becomes liquid. So, through this process the refrigerant does its phase change during this process, but here it also does the phase change, but at the same time it is continuously absorbed by another component and we call this as a absorbent. So, it is continuously absorbed and continuously also desorbed, means when it is absorbed the solution becomes strong, and when it is desorbed solution becomes weak. So, in a sense that means in a absorber unit there is a absorbent which absorbs this liquid and it forms a strong solution which is fed to generator, and side by side when it comes out from the generator this solution becomes weak, and only gas goes to the generator and solution and weak solution comes out of the generator. So, this is how it operates broadly in this thermal circuit. So, the first way that a vapor absorption system differs is the retrieving refrigerant vapor from a liquid solution. So, it involves heat transfer from a relatively high temperature source. Most of the energy sources is the low grade heat energy or alternative source of energy such as solar, geothermal, and to use this energy we are using a combination what we call as a generator absorber with a valve system. And also I have also mentioned that nature of the compression systems. So, here there is no compressor, it is replaced with a very small pump which takes minimal amount of energy, high grade energy, and in addition to that the refrigerant gets absorbed by a secondary substance which we call as a absorbent to form a liquid solutions and which is pumped to high pressure. The average specific volume of the liquid solution is less than that of refrigerant vapors. So, the work requirement is significantly less. So, in absorption refrigeration as an advantage of relatively small work input as compared to vapor compression system. Now, let us talk about some theoretical aspects. So, these particular things can be integrated in a manner that we will be able to find the thermodynamic estimates of COP for this kind of vapor absorption systems. So, the system is modeled in a way that this plant uses Qg amount of heat from the source T1 that goes to the generator, and it provides a refrigeration load QE, that means the space that is going to be cooled. The amount that heat is taken from the space is QE, and finally heat rejection takes place to the sink which is atmosphere that comes from the condenser and absorber. So, that is QC and QA, and they are maintained at temperature T2. Now, one can write the first law and equations. So, heat balance equation QE plus QG is equal to QC plus QA, the first equation. Second equation also tells that we can recall the entropy principle or law of entropy, where total entropy change of the system is always greater than or equal to 0. So, here the systems involved is the source, sink as well as the region which is getting cooled. And from this, if you can try to find out this entropy values and writing, and all this happens at constant temperatures, and so from this we can write down the basic equations of entropy in the form of Q and T. If you once you write that equation, so it, and also you have to take heat that comes out becomes negative, heat that goes out is taken as positive. So, in a sense that if you put this frame these equations, and ultimately and we can rewrite this, use these first law equations in the entropy equations once you put, and finally, we come up a relations which is Q E by Q G as a function of 3 temperatures, which is T 1, that is source temperature, T 2 which is sink temperature, and T R is the evaporator temperatures. And this Q E and Q E G is nothing but your COP. So, COP is less than T 2 minus T 1 by T 1 into T R by T 2 minus T R. One interesting thing you can see is that COP we have represented as a function of 2 parameters. One is T 1 minus T 2 by T 1. So, this is nothing but a efficiency of a Carnot cycle or heat engine. Other term that comes is T R by T 2 minus T R. So, it is nothing but the COP of a refrigerator. So, that means we can model these particular things, that when you calculate a COP of a vapor absorption systems, it can be modeled as a heat engine part, as a refrigerator part. So, if you look at this particular figure, the system can operate in a manner that whatever work that comes from the engine, we can get it utilized in the cyclic refrigerator, and through this we can maintain a condenser and absorber at certain temperature T 2, and the heat balance Q A and Q C, that means heat rejected from the heat engine and heat rejected from the refrigerator, that goes to a common unit what we call as a condenser and absorber unit. So, by virtue of this we can maintain a temperature T 2. So, this work input from the cycle in heat engine, that is nothing but your pump work that goes into the system, and at the end of the day what we get out of it is that we get a cooling load in the evaporator, that is Q E, that means it takes the heat from the space which is going to be cooled. So, for which the evaporator temperature is maintained as T R, and when you remove this inequality sign, we can obtain this COP, maximum COP of a vapor absorption systems, which is nothing but same system operating with a cyclic or you can say efficiency of a system which operates in a Carnot cycle or Carnot efficiency multiplied by Carnot COP of that cyclic refrigerator. Okay. So, the summary that we can get out of this analysis is that maximum possible COP in a vapor absorption unit is nothing but the product of ideal COP of a refrigerator working between T R and T 2 and ideal thermal efficiency of the engine working between T 1 and T 2. Now, while vapor compression refrigeration requires expenditure of high grade energy in the form of shaft work to drive the compressor, but it has a disadvantage of vibration and noise, and in that sense the absorption refrigeration requires low grade energy in the form of heat to drive it. So, it is relatively silent in operations and it is subjected to very little wear. Of course, since we are not using the high grade energy, the absorption unit has always a relatively low COP, but this particular concept or thought is being compromised by incorporating larger or big unit. Where we are using this? Because whenever there is a waste heat available for utilization such as solar energy, and so it is mainly implemented for food preservation and comfort cooling, where we have main thrust is utilization of waste heat or renewable energies. The practical utility of vapor absorption systems is one such unit is the ammonia water vapor absorption systems. So, what it does is that these systems and important things when you see this ammonia water vapor absorption systems, here the ammonia is used as a refrigerant and water is the absorbent, because there is a combination of ammonia and water is that ammonia gets absorbed in water very quickly. So, that combination you have to take the advantage of this, and that can that can be used as a vapor absorption unit, and of course, ammonia is also a good refrigerant. So, vapor absorption systems normally use a ammonia as one of the refrigerant. And of course, ammonia can be available in large quantity, because when you think about vapor absorption unit, you think about a big units of in terms of large installations. So, in a sense that for which you have to we require a large quantity of refrigerant, which is in this case is your ammonia. So, what happens is that how the system operates. If you look at this particular figure, there are 4 important units: condenser, generator, absorber and evaporator. So, the ammonia vapor which comes out from the evaporator, which is at state 1, is absorbed by the liquid water in a absorber, and this absorber is nothing but a heat exchanger. And this process is and because of this we will get a liquid solution, and this and here this thermodynamic process is exothermic, that means lot of heat is released. So, we require a cooling water to take out the heat, and when you take out this heat and you maintain that continuously, that absorber temperature remains constant, and the strong solution is now pumped to generator. So, there is a pump here, that what pump work I talk about is getting added here, and it is a minimal work, and when it gets added, the strong solution is fed to the generator. So, the vapor liberated from the state 2 passes in the condenser. Now, what happens in the generator? It interacts the high temperature source, heat is getting added, the strong solution, only vapor comes out from the generator and it goes to condenser, where heat is released. And finally, the refrigerant vapor that comes out goes into the expansion valve, and in the expansion valve, and once it pressure drops, so it goes to the evaporator and it takes the heat from the space which is going to be cooled. So, if you look at in a broad sense, there are 2 circuits. One is this particular circuit, we call this as a refrigerant circuit, where the flow of refrigerant is allowed. Here we have refrigerant as well as absorbent circuits, where you have refrigerant plus absorbent, and in this circuit only refrigerant flows. And to get these things to be a more concise manner, a common way of looking at ammonia water systems uses other components like rectifier, and also we have a heat exchanger which is placed between the generator and absorber unit, and this is used to modify the systems, and we say it is a modified vapor absorption systems. And the entire idea is that when heat is released, let us say in the absorber, so continuously how you are going to utilize this heat. So, one sense that the heat that refrigerant, that weak solution that comes from the generator to the absorber, it has a lot of heat. So, this heat is getting utilized to cool these pumped liquid strong solutions. So, that is a heat exchanger. So, from the absorber we have a strong solution that goes out. This strong solution gets preheated by taking the heat from this weak solution which is released from the generator at high temperatures. So, that is the where the heat is getting utilized and the system performance gets improved. Other way is that when you think about the refrigerant that goes to the condenser, we ensure that it is only refrigerant vapor. So, vapor that must go. Other things like since it is a solution, so we should not allow the water components or moistures which to get into the condenser. And in this particular circuit only we have refrigerant that circulates between the condenser and evaporator. But through this process, these 2 units, generator and absorber unit, takes about strong, make the refrigerant strong solutions or weak solution by continuous absorption or desorption. This is another versions of a plant flow diagram, which I have taken it from this book Peak and Lag Engineering Thermodynamics. So, here they also talk about so many things, like we have expansion valve, we have reducing valves, and just to regulate the pressures, and we have strong solutions, and we have weak solutions that comes from the generator. And many a times we also use brine in water to improve the system performance. So, very basic bottom line is only NH3 vapor goes into this refrigerant circuit and only goes to the refrigerant circuit. To improve the system efficiency, we have other devices like expansion valve and reducing valve. Okay. This is another modified diagram of this. The other version of vapor absorption unit is a lithium bromide water systems. So, here important aspect is that water here in this system is used as a refrigerant. So, that is the main important factor, and of course, lithium bromide is nothing but a salt, it is a solid form, but we have to prepare a solutions, because when it mixes with water we can prepare a solutions. And these salt solutions, lithium bromide being a salt, has a strong affinity to water, and because they operate at very low vapor pressure, so it absorbs water vapor very fast and it is released in the evaporators. Rest of the philosophy remains same as that of a ammonia water vapor absorption systems. Only difference is that it is water is used as a refrigerant. Other important aspect is that water has a limitations that we cannot cool it below 0 degree centigrades. So, when a lithium bromide water vapor absorption system is used in practice, it is only used for comfort cooling. So, where your cooling requirement is required something around maybe higher than 5 to 8 degree centigrades. So, it is a comfort cooling systems, and it can be used in combination as a cascade system with any other unit. Okay. Now, next topic that I am going to discuss is about refrigerants. So, till this point of time we have talked about vapor compression systems and vapor absorption systems, and in a vapor compression systems we have refrigeration systems and heat pump systems, and we all say that every system require a refrigerant. So, refrigerant when you are using, there are two categories of refrigerant that are fixed here, that when you say it is a vapor absorption systems, I already mentioned ammonia and water, these are the two refrigerants which are commonly used in the vapor absorption systems, and in fact these are inorganic compounds. But when you talk about vapor compression systems, the refrigerants of this nature may not seems to be a good alternative, because these units or vapor compression units normally or heat pump cycle, they use some kind of specific requirement for which low temperature is desired. So, in a sense that sometimes your temperature may be below 0 degree centigrades. So, for such applications we use specific refrigerant, and they are organic, those refrigerants are organic in nature. And of course, when you talk about those refrigerants, they have very specific properties, and those properties are required for the choice of a particular applications. So, the selection of refrigerant is very vital, because it is a working fluid for refrigeration and air conditioning applications, and it is based on basically three factors. One is performance, that means we should get the desired effect, and it has a safety, and it should have a environmental it will have a minimal environmental impact. And the performance I refer to cooling and heating capacity, and the safety issues are mainly due to the hazards of toxicity, flammability. Environmental factor mainly refers to that they do not harm the ozone layers in the atmosphere, and this environmental effect has another link to the climate change. And when you choose a refrigerant, the temperature of the refrigerant in the evaporator and the condenser for a vapor cycle is mainly governed by the temperature of cold region and hot region, and with which the system interacts thermally. And of course, their suitability is based on the pressure temperature characteristics. So, it is always desirable to have a very excess low pressure in the evaporator and excessively high pressure in the condenser. That is what we already solved the many things that evaporator, so that we can get a desired cooling effect without any hamper. Other aspects are chemical stability, corrosiveness and cost issues are also consideration for the refrigerant selections. And many a times what happens, the compressor unit. So, the compressor is available for a particular refrigerant, that means if what all you want to use this particular refrigerant, there is a specific compressor design. So, the type of compressor also affects the choice of the refrigerant. For example, centrifugal compressor are preferred for low evaporator pressure and refrigerants with large specific volume at low pressure, whereas reciprocating compressor perform better over large pressure range, but they have ability to handle only low specific volume refrigerants. So, these two, this is another important aspect for the choice of the refrigerant. Now, moving to the type of refrigerant that are used for refrigeration systems. Prior to 1930, there were only two classes of refrigerant we call as a synthetic refrigerants, and they come under chlorofluorocarbons or hydrochlorofluorocarbons. So, these are the categories and they are known as freons during that time, and about 50 number of inorganic and refrigerants were proposed for their applications. And inorganic type we have ammonia, which is mainly used for reciprocating and screw compressors, water, and it is used in the vapor absorption refrigeration for lithium with lithium bromide as a absorbent. And also we have another inorganic refrigerant which is carbon dioxide, and we also commonly known as a dry ice and mostly used in the transport refrigeration. So, when you deal with the nomenclature, we are going to classify in basically four broad categories. First thing, either they come under chlorofluorocarbons CFC, they come under hydrochlorofluorocarbons HCFCs, then hydrofluorocarbon HFCs and simple hydrocarbon HCS. And for all these case, although they are very difficult to remember, so they are given a trade names, either we call this as a refrigerant R or freons, and they are supported with these numbers and they are supported with a number, and we will talk about those numbers later. So, for and let us say CFC 11 or F 11, R 11. So, F stands for trade name, F or R stands for trade name, and 11 stands the number which is design. So, instead of CFCs, CFS, SCFC, CFC, SCFC, all these numbers when you use those refrigerants, then what it says is that it has either it is represented by its chemical compound or it can be represented by its trade name. And with respect to trade name, they are most commonly known, because with respect to their trade name, the compressor units gets specified. For example, if you say you want to centrifugal compressor in AC systems, R 11 or F 11 is a common choice, although of course, another unit could be, another number could be R 113 can be common choice for centrifugal compressors. But when you move to the reciprocating compressors, then R 11 may not be a good choice, rather R 12 may be another choice. And for rotary compressors, we can have R 114. And for heat pump systems, one particular refrigerant could be R 142B. And there are other class of refrigerants we call as azeotopes R 502, and those azeotopes are kind of a design of new refrigerants which takes the mixture of hydrochlorofluorocarbons and chlorofluorocarbons. For example, azeotopes R 502 is a mixture of 48.8% of R 22 and 51.2% of R115, and they are mostly used in the large supermarkets. Okay, these are the common names. Now, I am going to talk about what is this R and how this the refrigerants are designated. So, there are two categories. One is first category is the saturated type hydrocarbon, and they are denoted as, and then when you say saturated hydrocarbons, it consists of hydrogen, carbon. In addition to that, we have fluorine as well as chlorine, and the combination of those things is Cm, Hn, Fp and Clq, and for this particular equation seems to be valid. Valid why? Because by virtue of their characteristics or bond or affinity, N plus P plus Q is equal to 2m plus 2. When they are satisfied, then only we can say it is a saturated hydrocarbon. So, if this is your refrigerant and I want to assign it as a trade names, either I can use R or F. So, that is what I am, it is mainly mentioned here R, and R m minus 1 and n plus 1 and P. So, for this particular refrigerant chemical name, the trade name becomes R m minus 1 n plus 1 P. So, by these things we can say C2Cl2F4 is R114. So, basically when you say R114, which means your m minus 1 is 1 because first unit, second is n plus 1 is equal to 1 and 4 is P is equal to 4. So, this will take you m is equal to 1, n equal to 0, P is equal to 4. When I say this, so we have to say that n plus P plus Q is equal to 2m plus 2. So, this 2m is 1 means this is 4 and n is 0 plus P is 4 plus Q is equal to 4. So, Q is equal to 0. So, we know all these things. So, we can write this thing is that m is equal to 2. So, m is equal to 2 means 6. So, Q is equal to 2. So, Q is equal to 2. So, m is equal to 2, n is equal to 0, P is equal to 4, Q is equal to 2. So, from this m is equal to 2 means carbon 2, n is equal to 0 means there is no hydrogen, F is equal to P is equal to 4 means F4 and Cl chlorine is 2. So, this is how it is written here. So, accordingly for all other cases you can write this. So, another important point is when you talk about R12, but here there are 3 numbers here and this is 2. So, in that case when you talk R12, we have to rewrite is at R012, and when you say R012, then we have to work like this: m minus 1 is equal to 0, n plus 1 is equal to 1 and P is equal to 2. So, that means m is equal to 1, n is equal to 0, P is equal to 2. So, Q can be found out as Q is equal to 2m plus 2, that is 2 plus 2 4 minus 2 is P and that is equal to 2 because n is equal to 0. So, from this we can find out this refrigerant would be CCl2 and F2. So, likewise all other refrigerant we can note it this way. And there are other category of refrigerant which are brominated refrigerants, they are denoted by putting an additional B, and to know that the chlorine atom is replaced with a bromine atom. So, basically we have to start the problem CF3Br means one chlorine atom is replaced with a bromine atom. So, they are brominated refrigerant. This is the next category of refrigerant is unsaturated compounds. For unsaturated compounds, their chemical formulas are CM, HN, FP, ClQ, and where N plus P plus Q is equal to 2M. So, these things must be satisfied for the compound to be a unsaturated one. And here important thing is that it is a denotation is 4 numbers. There are 4 numbers here. When there are 4 numbers, one can recall that it is a unsaturated compound. So, R has no meaning, the first one has no meanings. So, for example, if I say R 1 1 5 0, so first R 1 remains as it is. So, 150 means your M minus 1 is equal to 1, N plus 1 is equal to 5, and P is equal to 0. So, this means M is equal to 2, N is equal to 4, and P is equal to 0. So, Q is can be found out 2M minus N minus Q P. So, this is 4 minus 4 minus 0. So, Q is 0. So, from this we can now say that Cm, that is C2 H N, N is 4, F P, that is 0, Cl Q, that is 0. So, it is C2 H4, which is here. So, this is we have got saturated and unsaturated compounds, and they are organic compounds. The other inorganic compounds, the inorganic refrigerants, we have choices ammonia, we have water, and we have carbon dioxide. There are 3 choices of refrigerant. So, for that the standard designation will be 700 added to this molecular weight. For example, if I say R 718, so 18 is molecular weight of water. So, 700 when it added to 18, so R 718, so it is a water. So, this refrigerant is a water. Similarly, for CO2 it is 744, R 744. So, this is how the refrigerants are designated. And the last part of this refrigerant is the environmental issues. So, till this point of time there are compelling scientific data that indicates that release of chlorine containing refrigerant into atmosphere is harmful, and this because this released refrigerant deplete the stratosphere ozone layer and they contribute global climate change. For this, a quantitative parameter is formed which says that which is say that what we call as a GWP, global warming potential, and over last 100 years this particular GWP was estimated for different refrigerants, and it is found that when you use CFC category refrigerant like R12 or R114, their GWP is about higher than 10,000. But when you use HCFC type of refrigerant or HFC type of refrigerant, their GWP is about more than 1000. So, this refrigerant is to be discarded. So, the common choice is that we have to design our new refrigerants. So, the new refrigerant that come under propane, methane, butane, which are little bit which are much better than this CFC type refrigerant. Other choice is that we have to use the gases like carbon dioxide, ammonia, methane. These are very less threat for the global warming. So, these are mostly used refrigerants in practice. Okay. With this, I come to the end of this segment of this lecture. So, we will try to solve some problems. So, till this point of time there is no major requirement of problems as far as the vapor absorption is concerned, but I will try to sum it up some of the vapor compression systems which we have already discussed in the last class, and some important point that I need to emphasize, how to include exergy in the vapor refrigeration systems. So, to have some kind of application that how you calculate exergy in a vapor compression systems, I have included this particular problem. So, let me start this problem which involves the calculation of exergy lost due to irreversibility. Now, in a vapor compression system, the irreversibility mainly comes to one thing, one is in the expansion valve, other is in the compression. In addition to that, your evaporator and condenser temperatures, they are operated at different temperatures than that of the space a warm region or the space to be cooled. So, let me start the first problem. So, the vapor compression cycle operates between the cold region, that is 0 degree centigrade, and warm region 26 degree centigrade, uses the refrigerant R134A as a working fluid. Remember, this is the same problem which was discussed in the last lecture, but here the emphasis was given something different, is that here we want to introduce irreversibility into the systems. The irreversibility is introduced by this, the saturated vapor enters the compressor at minus 10 degree centigrades, and remember your cold region was 0 degree centigrade, but your evaporator temperature is minus 10 degree centigrade. Liquid leaves the condenser at 9 bar and 30 degree centigrades. So, here by these things there are two parameters. Normally liquid leaves the condenser at saturated liquid, but we have specified it is at 9 bar and 30 degree centigrades. So, here another irreversibility comes into picture, that this particular state could be a subcooled region, and we have to calculate the mass flow rate of the refrigerant. So, first thing and of course, another point is that when saturated vapor enters the compressor at minus 10 degree centigrades, but it we do not know where it leaves. So, it leaves probably at 9 bar, but we do not know what pressure it leaves at 9 bar, but what enthalpy or entropy we do not know. So, this is where of course, we need to give, we have to introduce isentropic efficiency of the compressor. So, let me put this isentropic, the missing data of the compressor, let us say 80%. So, the solution can be stated like this. So, first we have to draw this temperature entropy diagram. So, we have to create a dome. So, we have to draw the cycle first. Of course, we have subcooled region here. So, first thing we have to denote the states, entry to the compressor, and if the process needs is isentropic, it would have gone this. So, it would have reached 2s, and this constant pressure is at 9 bar, but the condenser the exit of the condenser it is 30 degree centigrade, but remember it is your warm region is 26 degree centigrade. So, somewhere you have 30 degree centigrade. So, nowhere, so this point 3 would be located here and 4 would be here, and we do not know the location of 4, and we also know that there is a isentropic efficiency of the compressor is 82%. So, 2 will be here. Now, to solve the problems you have to go state by state. So, let us see state 1. So, state 1 we can say it is at minus 10 degree centigrade, and of course, you have this evaporator temperature is minus 10 degree centigrade, but your warm region is above it, that is 0 degree centigrade. So, T H hot region, T C cold region is 0 degree centigrade. Okay. So, this is the very basic TS diagram that we can draw. So, state 1 is minus 10 degree and it is saturated vapor. So, when it is saturated vapor for 10 degree we can refer this particular table, we have data at minus 8 and minus 12 degree centigrade. So, all these data needs interpolations, enthalpy, entropy. So, by interpolating this data at state 1 we can find out H 1 as 241.35. In fact, yesterday also we calculated these values, and S 1 is 0.9253 kilojoule per kg Kelvin, and since S 1 is equal to S 2 S, that is 0.9253 kilojoule per kg Kelvin, and efficiency, isentropic efficiency of the compressor we can write as H 2 S minus H 1 divided by H 2 minus H 1, and that is 0.8. So, from this we have H 1, we have entropy H 2 S, and from this data we can find out P 2 state 2 at P 2 9 bar, H 2 S 0.9253. This will give you H 2 S as in this value. So, you can say 271.25 kilojoule per kg, and from this equation we can now find out H 2, because we know H 2 S, you know H 1. So, this H 2 will give you can be calculated as 278.7 kilojoule per kg. So, we know H 2, but we do not know S 2. Again we know S 2 S, but we do not know S 2. So, the S 2 will be required for calculation of exergy destruction. So, from this we can now calculate at P 2 9 bar and H 2 278.7 kilojoule per kg. So, this will give you S 2 is equal to 0.9566. So, that means 9 bar close to 278, I have just taken 282. So, I can say close value will be 0.9566 kilojoule per kg Kelvin. So, we know state 2. Now, state 3 we can say this is at 9 bar 30 degree centigrade. So, 30 degree centigrade I can say it is a subcooled region. So, from this subcooled region we can calculate this H 3 as 91.49 kilojoule per kg, and this is nothing but your H 4. Of course, we can now calculate H 3. H 3 is 0.3396 kilojoule per kg Kelvin. This is required for calculation of exergy. Then state 4. So, state 4 we have this equation x 4 is equal to H 4 minus H F 4 divided by H g or H F g 4. Okay. So, here H 4 is known, H F 4 we can calculate at minus 10 degree centigrades. So, H F 4 is already there, 36.97 kilojoule per kg. So, this is taken at average of these two, and H 4 is equal to 91.49 kilojoule per kg. So, this is already here. Now, H F G 4 is 204.39 kilojoule per kg. So, this is calculated based on the interpolation of data of these two values. So, from this now we can say x 4 can be calculated as 0.2667. So, this is required here for the next data. So, once you say this x 4, we can now say what is the value of S 4. So, S 4 is equal to S F 4 plus x 4 into S F G 4. So, this is equal to S F 4 you can calculate at state point 1 by interpolation of data. So, this value would be somewhere average of this. So, this will be 0.1486 plus x 4 already calculated 0.2667, then 0.9253 minus S g minus H f means 0.92553 minus 0.1486. So, this number is 3557 kilojoule per kg Kelvin. So, now after this evaluation you have to go one by one. First, compressor power, W dot C is equal to m dot into H 2 minus H 1. So, this is 0.09 into 278.7 minus 241.35. So, this value is 3.36 kilowatt. Then refrigeration capacity Q dot in is equal to m dot into H 1 minus H 4. So, that is equal to 0.09 into H 1 is 241.35 minus 91.49, that is equal to 13.48 kilowatt, and this is equal to 3.85 TR, third one COP beta is equal to W Q in by W net, that is equal to 13.48 divided by 3.36. So, this value is close to 4. Last one is rate of exergy destruction. The rate of exergy destruction has two parts. One is that means exergy Xc is equal to nothing but m dot T 0 into S 2 minus S 1, if you recall this formula. So, here X E for expansion valve, that is equal to m dot T 0 into S 4 minus S 3. So, and here m dot is 0.09, T 0 is we can say 26 degree centigrade, which is ambient. So, 299 Kelvin. S 4 already we have calculated 0.3557 minus S 3 0.3396. These values were calculated already. So, this is 0.433 kilowatt. So, expansion valve exergy is this. Other thing that we have is for compressor. So, that compressor you can calculate m dot T 0 into S 2 minus S 1. So, that is 0.09 into 299 into S 2 minus S 1 is 0.9566 minus 0.9253. So, this value is 0.842 kilowatt. So, exergy destruction in the expansion valve is 0.433 kilowatt, exergy destruction in the compressor is 0.842 kilowatt. Now, if you actually quantify, WC is already calculated 3.36 kilowatt and Xc by W dot C, it roughly about 0.25, and X expansion valve divided by WC, this is roughly about 0.13. So, 13% of exergy is lost in the expansion valve and 25% of exergy is lost in the compressors. Okay. This is how we solved about the vapor compression systems. Now, I will switch over to another problem which we discussed in this particular class. It is a aqua ammonia vapor absorption refrigeration systems, in which heat is supplied to the generator by a condensing stream with 90% quality at 2 bar. So, the temperature in the refrigerator is minus 10 degree centigrade, while ambient temperature is 30 degree centigrade. We have to calculate maximum COP, and if the actual COP is 35% of the maximum value, we have to estimate the amount of steam flow rate required for refrigeration load of 30 TR. So, for example, you have to recall this particular diagram, in which these systems can be modeled as a that means COP of the system can be modeled as a cyclic heat engine and cyclic refrigerator, and for which we have already derived COP max as T 1 minus T 2 into T r divided by T2 minus Tr into T1. So this is how we have modeled, and here what are known to us? T1 is steam at 2 bar, so it is saturated. So from steam table we can find out T saturated temperature as 120.2 degree centigrades, and of course that point of time your HFG is 2201.9 kilojoule per kg. So here T saturated is nothing but your T1. T2 is ambient, that is 30 degree centigrade, 303 Kelvin. Tr evaporated temperature minus 10 degree centigrade, that is 263 Kelvin. So from this equation we can say maximum COP will be, putting this number 122.2 plus 273 becomes 393.2 minus 303 multiplied by Tr 263 divided by T2 minus Tr 303 minus 263 into T1 is 393.2. So COP max, which is asked here, can be calculated as 1.5. So the second part, this is that if your actual COP is 35% of this maximum COP, then we can write simply as COP is 1.5 into 0.35. So this is 0.525, and this maximum this COP can be now written as QE by QG, that is equal to 0.525, and from this we can calculate QE is your 30 Tr, that is evaporator load 105.6, and that is kilowatt, and from this we can now calculate Qg becomes 176 kilowatt. Okay. So from this QE and Qg, one should say this is kilowatt, but we require steam flow. So to the steam flow we have to use this, what is the steam quality. So steam quality is 90% of this. So actual enthalpy values, so we can say heat transfer from steam would be 0.9, which is the quality of the steam, multiplied by its enthalpy 2201.9. So this value is 1981 kilojoule per kg. So this steam flow rate would be known, that is m dot would be amount that is available, that is heat that is required 176 kilojoule per second, divided by steam heat transfer from the steam 1981 kilojoule per kg. So m dot can be now 0.08 kg per second. So this is the amount of steam that is required for refrigerant load of 30 Tr. So this is how you are going to solve these problems on vapor absorption systems. Only for this particular course only this kind of problems are normally referred. We are not going very deep into the because we are not going deep into the vapor absorption refrigeration systems. And here one more thing is that when you think about aqua ammonia absorption systems, of course, we have to recall the steam table. So, steam table data is very vital to get some temperatures in particular for the generator, and that is what it is used here, that steam table was used for to calculate the saturated temperature for water which is at 2 bar. Okay. With this I conclude this lecture. Thank you for your attention.